In this part of the course, we will be emphasizing the bijective paradigm in combinatorics, which means that in order to prove combinatorial formulae, we will try to create bijections between sets representing the left-hand side and the right-hand side of the formula. And one of the most important tools here for converting combinatorial formulae into set theoretic bijections is the notion of a combinatorial class. So what is a combinatorial class? A combinatorial class consists of two things. The first is a finite or countably infinite set. Let's say script A. And the second thing is that this set A comes equipped with a size function. And we'll denote the size function by alpha goes to mod alpha for each alpha in A. And this size function is a function from A to non-negative integers. So to each element of A, we will attach a size of alpha, which we denote by absolute value of alpha. And this has to be a non-negative integer. And there is one condition such that for every n in every non-negative integer n, the set A subscript n consisting of elements of size n, alpha belongs to A, such that size of alpha is equal to n. This set is finite. Okay, in the sense that this combinatorial class allows us to count its objects by size. And so once you have a combinatorial class, you can talk about its counting sequence. It is the sequence. An is just the size of An, cardinality of An. And the ordinary generating function of A. Here ordinary is used to emphasize the fact that this is not an exponential generating function. We will encounter exponential generating functions a little later in the course. Is the formal power series. You could of course try to treat it as an analytic function, but in this course we will not. A of x is equal to summation n goes from 0 to infinity an x to the power n. Okay, let's look at some examples. So let's just look at W to be the collection of all binary words. By binary word, I mean word in the alphabet. Let's say A for alphabet, it has two elements, 0 and 1. So this W consists of, firstly there's the empty word, which is usually denoted epsilon. Then there are two words of length 1, 0 and 1. There are four words of length 2, namely 0, 0, 0, 1, 1, 0, 1, 1. And then there are words of length 3. There are 8 of them. And you can go on. And the length of the size of a word is just defined to be the length, i.e. The number of letters in the word. So this is a word of length 0, 0, 1, 1. This is of length 3. And so of course here we'll have that Wn, the size of the cardinality of words of length n. This is just going to be 2 raised to n, because each of the n letters of your word you can choose to be 0 or 1. And the generating function Wx will be summation 2 raised to n x to the power n, which is n goes from 0 to infinity, which is nothing but 1 over 1 minus 2x. Let's look at a second example. S will be the set of all permutations of size n. So permutation of size n is just a bijection sigma from n to n. And usually we write permutation in one line notation. So permutation is written as sigma 1, sigma 2, sigma n denotes a permutation of size n. So for example, S0 is just going to be permutations of the empty set. And so it's just, well, you can think of the empty permutation as the only element of S0. S1 is all bijections from the set with one element, namely 1, to itself. So that's just the singleton 1. S2 is, there's the permutation 1, 2, and there's the permutation 2, 1. S3 has 6 elements, 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. And in general, Sn, which is the cardinality of Sn, is going to be n factorial, and the ordinary generating function of this combinatorial class is going to be Sn summation n goes from 0 to infinity n factorial x to the power, s of x, I should say, x to the power n. And this power series, if you were to treat it, try to write an analytic function, it would not have a positive radius of convergence. However, it is perfectly fine as a formal power series. And now let's come to a very interesting combinatorial class, which is the Catalan class, or rather the class of all triangulations. C is the class of triangulations of a regular polygon with n vertices. So here for each n we fix one regular polygon. Maybe you can take it to be the nth roots of unity in the complex plane, and then try to write down all its triangulations, not with n vertices, with n triangles. So we'll see the relation between the number of triangles and the number of vertices. So Cn is the set of triangulations, and C is the class of all triangulations. The size of a triangulation is the number of triangles in it. So for example, C1, there's only one triangulation of a regular polygon with one triangle, namely you take the triangle itself. So you take this triangle and it is already a triangle, you don't need to add any diagonals. What about C2? Well, C2 has, so you take a regular quadrilateral, and here I'm taking sort of, you can imagine these to be the fourth roots of unity. And let's see how we can triangulate it. So we can triangulate this in two ways. Either we join these two to give us an edge, or we join these two. So there are two triangulations of with two triangles, and these are triangulations of a quadrilateral. To get triangulations with three triangles, we will be triangulating a pentagon. So what I'll do is I'll draw a pentagon. And since I'll be triangulating this several times, let me just copy it out. So the first triangulation I can do is something like this. I'll just take this vertex and join it to these two. The next I can do is I can take this vertex and join it to these two. And then the next is I can take this vertex and join it to these two. I can take this vertex and join it to these two. And I can finally take this vertex here and join it to these two. And that's about it. Once I choose a vertex and join it to something, then I have two choices. I have a quadrilateral left. I have two choices. Either I join this original vertex to another one, or I do this. But both cases, if I were to choose this instead of this, then I would get back this triangulation here. So they are not really going to give me different ones. So you should convince yourself that there are only 5 of these triangulations. And you can go ahead and try to draw all the triangulations of a regular hexagon. But what I'll do now is instead I'll prove that the Cn, the number of triangulations with n triangles, satisfies the same recurrence relation that is satisfied by Catalan numbers, namely C0 is equal to 1 and Cn is summation k plus l equals n minus 1 ck cl. And how do I prove that? Well, let's start with some large polygon. So I have many vertices, and for definiteness I will pick so if we are thinking of these as the nth roots of unity, I could, for example, pick so let me just join these, and if they're nth roots of unity, I will have a distinguished vertex, namely 1, and I can fix that, and I can in fact choose a distinguished edge, namely the edge joining that to the next edge. So that's my distinguished edge, and this edge must be part of some triangle. So this edge must be part of some triangle. Let's say it's this one. It's got to be, these both will be connected to some common vertex in our triangulation, and the remaining vertices will somehow form some other triangulation. So here's one triangulation, and here's let's see, another triangulation. So what I've done is I've broken up my original triangulation into two parts canonically. So I had this original triangulation, and now from that I have constructed this red triangulation of this half and a black triangulation of this half. And there's only one triangle that's missing from both, and that's this triangle here in the middle. So totally I have two triangles, and the total size is one less than the original triangulation, and that is exactly so this whole thing is Cn, and this black and red pair is a Ck times Cl, where k plus l add up to n minus 1. So I can just if I wish, I can just take this piece and cut it out. And this is, let's remove this, that's one triangulation, and I have that plus another triangulation, which is this other piece over here. And that sort of bijectively realizes this Cn is equal to k plus l equals n minus 1 CkCl.